Hello there. Tonight, we are going to explore the most relaxing cosmology facts to help you fall into a deep, restorative sleep. Imagine, if you will, the absolute nothingness that preceded everything. A silence so complete that even the concept of silence itself had not yet been born. A darkness so profound that light was not absent, but simply impossible. We are about to drift backward through the corridors of deep time, past the formation of galaxies, past the first stars, past even the primordial atoms, until we arrive at the very threshold of existence itself, where the universe took its first breath and time began its eternal march forward. There was a moment, though moment is perhaps the wrong word, for time itself did not exist, when all of space, all of matter, all of energy, every future galaxy and star and planet and atom existed compressed into a point smaller than the smallest thing you can imagine. Physicists call this the singularity, a mathematical concept so extreme that our equations break down when we try to peer into its nature. Imagine trying to divide by zero, or to comprehend infinity not as an endless expanse, but as a singular, infinitesimal point of infinite density and infinite temperature. Within this point, there were no dimensions, no up or down, no before or after. The laws of physics as we understand them, gravity, electromagnetism, the strong and weak nuclear forces, were unified into a single, incomprehensible force. This was not a place in space, because space did not exist. It was not a moment in time, because time had not yet begun. It was pure potential, the cosmic seed from which everything would unfold, waiting in a state of perfect, timeless equilibrium. And then, for reasons we may never fully understand, that equilibrium shattered. In the first trillionth of a trillionth of a trillionth of a second after the Big Bang, a span of time so brief that it makes a blink of an eye seem like an eternity, the universe underwent a period of exponential expansion known as cosmic inflation. During this incomprehensibly rapid growth, space itself stretched faster than the speed of light, ballooning from something smaller than a subatomic particle to something roughly the size of a grapefruit, and then continuing to expand at a slightly slower but still staggering rate. This was not matter moving through space. This was space itself being created, woven into existence from the quantum foam. Imagine a balloon being inflated, but instead of air filling a rubber shell, the very fabric of reality is being stretched and multiplied, creating new dimensions, new distances, new possibilities. In this first instant, the universe was unimaginably hot, far hotter than the core of any star that would ever form, and filled with a roiling sea of energy so intense that particles and antiparticles flickered in and out of existence in violent quantum fluctuations. There were no atoms yet, no molecules, no structures of any kind. Just pure energy in its most chaotic and primordial form, expanding outward into the void it was simultaneously creating. As the universe continued to expand, it began to cool, and in that cooling, something extraordinary happened. Energy began to condense into matter. According to Einstein's famous equation, E equals mc squared, energy and matter are interchangeable, two sides of the same cosmic coin. In the first moments after the Big Bang, the universe was so hot that matter could not exist in any stable form. Particles would form and immediately annihilate with their antiparticles in bursts of pure energy. But as the temperature dropped, the balance shifted. Quarks, the fundamental building blocks of protons and neutrons, began to bind together under the influence of the strong nuclear force. Within the first microsecond, These quarks formed protons and neutrons, the particles that would eventually make up the nuclei of all atoms. For a brief period, the universe was a dense, hot soup of these particles, colliding and interacting in a chaotic dance. And yet, even in this chaos, there was a subtle asymmetry, a tiny imbalance between matter and antimatter that meant when particles and antiparticles collided and annihilated, a small fraction of matter remained. This imbalance, this cosmic quirk, is the reason anything exists at all. Without it, the universe would have annihilated itself in the first moments, leaving nothing but a faint glow of radiation expanding into emptiness. For the first 3 minutes of the universe's existence, conditions were just right for nuclear fusion to occur on a cosmic scale. The temperature had dropped enough that protons and neutrons could stick together without being immediately torn apart by collisions. But it was still hot enough for fusion reactions to proceed. During this brief window, the first atomic nuclei were forged, primarily hydrogen, the simplest element with just one proton, and helium, with 2 protons and 2 neutrons. Trace amounts of lithium and beryllium also formed, but the universe was expanding and cooling too quickly for heavier elements to be created. This process, known as Big Bang nucleosynthesis, set the initial chemical composition of the cosmos, roughly 75% hydrogen and 25% helium by mass, a ratio that persists in the oldest stars and gas clouds we observe today. These nuclei were not yet atoms, though. They were bare, stripped of electrons, floating in a sea of free electrons and photons. The universe was still far too hot for electrons to bind to nuclei and form stable atoms. Instead, it was a glowing, opaque plasma, a cosmic fog where light could not travel freely but was constantly scattered and absorbed by the charged particles, swirling through space. For the next several 100,000 years, the universe was dominated by light. Photons, particles of electromagnetic radiation, outnumbered matter particles by billions to 1, and they filled every corner of space with their energy. This era, known as the photon epoch, was a time when the universe was a brilliant, incandescent fog, glowing with the heat of its own creation. The temperature was still thousands of degrees, hot enough to keep electrons from binding to atomic nuclei, and so the cosmos remained a plasma, opaque and radiant. Light could not travel far before being scattered by a free electron, and so the universe had no clear structures, no shadows, no dark corners, just an all-encompassing glow. Imagine being suspended in a luminous mist, where every direction you look is filled with the same soft, diffuse light, where distance has no meaning because you cannot see more than a few meters in any direction. This was the state of the universe for hundreds of millennia, a timeless, formless expanse of energy and potential, waiting for the next great transformation. And as the universe continued to expand, the temperature continued to fall, degree by degree, century by century, until finally the conditions were right for the fog to clear. Approximately 380,000 years after the Big Bang, the universe had cooled to a temperature of about 3,000 degrees Kelvin, still hotter than the surface of many stars, but cool enough for a critical transition to occur. Electrons, which had been zipping freely through space, began to slow down, and as they slowed, they were captured by the atomic nuclei that had been waiting since the first 3 minutes. Protons captured electrons to become hydrogen atoms. Helium nuclei captured electrons to become helium atoms. This process, known as recombination, marked the birth of the first neutral atoms in the universe. And with this transition came a profound change. The universe became transparent. Before recombination, Photons were constantly scattered by free electrons, trapped in an endless cycle of absorption and re-emission. But once electrons were bound into atoms, photons could travel freely, unimpeded, across vast distances. The cosmic fog lifted, and for the first time, the universe had a clear line of sight. The light that was released at this moment, the afterglow of recombination, has been traveling through space ever since, cooling and stretching as the universe expands, until today it reaches us as the cosmic microwave background radiation, a faint whisper of that ancient glow. The oldest light we can observe. After the light of recombination faded, the universe entered a period known as the Cosmic Dark Ages. For hundreds of millions of years, there were no stars, no galaxies, no sources of light beyond the fading afterglow of the Big Bang. The universe was filled with vast clouds of hydrogen and helium gas, drifting slowly through the expanding void, pulled together by the invisible hand of gravity. These clouds were dark, cold, and silent, a cosmic wilderness waiting for the first spark of light to ignite. Imagine a world without a single candle, without a single fire, where the only illumination comes from the faint, cooling embers of a long extinguished blaze. This was the state of the cosmos for eons, a time of quiet accumulation, as gravity worked patiently to draw matter together, creating denser and denser pockets of gas. Within these pockets, the seeds of the first stars were forming, though it would take millions of years for them to grow large enough and dense enough to ignite. And so the universe waited, suspended in darkness, the stage set for the next great act in the cosmic drama. Eventually, in the densest regions of the primordial gas clouds, gravity's patient work reached a critical threshold. The pressure and temperature at the core of these collapsing clouds grew so intense that hydrogen nuclei began to fuse into helium, releasing tremendous amounts of energy in the process. The first stars ignited, and the universe was illuminated once more. These were not stars like our sun. They were massive, brilliant, and short-lived, burning through their fuel at a prodigious rate. Astronomers call them population 3 stars, and though none have ever been directly observed, they existed so long ago that their light has not yet reached us, or has been lost in the vastness of space. We can infer their properties from the chemical signatures they left behind. These first stars were made almost entirely of hydrogen and helium, with virtually no heavier elements, because no previous generation of stars had existed to create them. They shone with a fierce blue-white light, and their surfaces were tens of thousands of degrees hot. And when they died, as all massive stars must, they did so in spectacular fashion, exploding as supernovae and seeding the surrounding space with the first heavy elements, carbon, oxygen, iron, and all the building blocks of planets and life. In their death, they gave birth to the chemical diversity of the universe. As more and more stars ignited, they began to cluster together under the influence of gravity, forming the first galaxies. These early galaxies were small and irregular, nothing like the grand spiral and elliptical galaxies we see today, but they were the beginning of the large-scale structure of the universe. Within these galaxies, stars were born and died in rapid succession, each generation enriching the interstellar medium with heavier elements. Gas clouds collapsed to form new stars, and those stars in turn exploded and scattered their enriched material back into space, where it would be incorporated into the next generation. This cycle of birth, death, and rebirth continues to this day, a cosmic recycling program that has been running for over 13 billion years. The light from these first galaxies began to ionize the surrounding hydrogen gas, creating bubbles of ionized material that grew and merged, eventually filling the entire universe. This period, known as the Epoch of Reionization, marked the end of the Dark Ages and the beginning of the universe as we know it, a cosmos filled with light, structure, and the raw materials for complexity. Of all the light in the universe, the oldest we can directly observe is the cosmic microwave background, the afterglow of the Big Bang, released at the moment of recombination. This light has been traveling through space for 13.8 billion years, and in that time, the expansion of the universe has stretched its wavelength from visible light to microwaves. Today, it fills the entire sky with a faint, uniform glow, detectable only with sensitive radio telescopes. When scientists map this radiation, they find it is remarkably uniform, with a temperature of 2.725 Kelvin above absolute zero, the same in every direction to within a few parts in 100,000. But within that uniformity, there are tiny fluctuations, subtle variations in temperature that correspond to slight differences in density in the early universe. These fluctuations are the seeds of all structure. The regions that were slightly denser than average would go on to collapse under gravity to form galaxies, stars, and planets, while the regions that were slightly less dense would become the vast cosmic voids. In this ancient light, we can see the blueprint of the cosmos, the initial conditions that set the stage for everything that would follow. It is a snapshot of the universe as it was 380,000 years after the Big Bang, a baby picture of creation itself. And so, from the primordial silence, the singularity before time, the inflation of space, the cooling and condensing of energy into matter, the forging of the first elements, the birth of atoms, the Dark Ages, and the ignition of the first stars, the universe emerged into the light. But even now, in the spaces between the stars, in the vast voids between galaxies, there is a profound silence, a stillness that echoes the original nothingness from which everything came. This silence is not empty. It is filled with the faint hum of the cosmic microwave background, the whisper of dark matter, the subtle stretching of space itself. It is a reminder that the universe, for all its grandeur and complexity, began in simplicity, in a moment of pure potential, and that the story of creation is still unfolding, still expanding, still cooling, still evolving. As you drift towards sleep tonight, let yourself float in that primordial silence, in the space between the first breath and the next, in the eternal now that connects the beginning of time to this very moment. Rest in the knowledge that you are made of stardust, forged in the hearts of ancient suns, and that the same forces that shaped the cosmos also shaped you. Sleep well and dream of the infinite. As we drift deeper into the architecture of existence, we find ourselves contemplating not the stars themselves, but the spaces between them, the vast, intricate network of invisible threads that connects every galaxy, every cluster, every supercluster across the observable universe. This is the cosmic web, a structure so immense that it defies human comprehension, yet so delicate that it can only be detected through its gravitational influence on the matter we can see. Tonight, we will trace these filaments of dark matter and gas, following them from the smallest nodes to the largest voids, and in doing so, we will discover that the universe is not a random scattering of stars, but a carefully woven tapestry, a cosmic lace stretched across billions of light years of space. For most of human history, we believed the universe was essentially uniform, that if you looked at a large enough volume of space, it would appear the same in every direction, with stars and galaxies distributed more or less evenly. But in the 1980s, when astronomers began mapping the positions of thousands of galaxies in 3 dimensions, they discovered something astonishing. Galaxies are not scattered randomly through space, but are organized into a vast interconnected network of filaments, walls, and voids. The first major survey to reveal this structure was the CFA Redshift survey, which mapped the positions of galaxies in a slice of the sky and found that they formed a pattern resembling a cosmic web, with long, thin filaments of galaxies surrounding enormous empty regions called voids. This was a revolutionary discovery, one that fundamentally changed our understanding of cosmic structure. The universe, it turned out, has a skeleton, an invisible scaffolding made of dark matter that guides the distribution of visible matter, shaping the locations of galaxies and clusters over billions of years. This web is not static, it is dynamic, evolving over time as gravity pulls matter along its threads, causing galaxies to flow like water through the cosmic rivers, converging at the densest nodes and avoiding the emptiest voids. The filaments of the cosmic web are the largest coherent structures in the universe, stretching for hundreds of millions of light years across the void. These are not solid objects, but rather concentrations of dark matter and gas, regions where the density of matter is slightly higher than the surrounding space. Along these filaments, galaxies form and cluster, drawn together by the gravitational pull of the dark matter that dominates the mass of the structure. Imagine a spider's web with thick strands connecting the anchor points, and you will have some sense of what the cosmic web looks like on the largest scales. But unlike a spider's web, which is 2-dimensional, the cosmic web is 3-dimensional, with filaments intersecting and branching in all directions, creating a complex, interconnected network. These filaments act as highways for matter, channeling gas and dark matter from the voids toward the nodes where galaxy clusters form. As gas flows along these filaments, it heats up due to compression and friction, reaching temperatures of millions of degrees and emitting faint X-rays that can be detected by space telescopes. This hot gas is difficult to observe directly, but its presence has been confirmed through careful measurements, revealing that the filaments are not empty corridors, but active regions where matter is constantly in motion, flowing toward the gravitational wells at the intersections. At the intersections of the cosmic web's filaments, where multiple strands converge, we find the nodes, dense concentrations of matter where galaxy clusters form. These are the most massive gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, along with vast amounts of hot gas and dark matter. The largest of these clusters can have masses equivalent to 1,000,000 billion suns, and they exert such a strong gravitational pull that they warp the fabric of space-time around them, bending the light from more distant galaxies in a phenomenon known as gravitational lensing. Within these clusters, galaxies orbit around the common center of mass, moving at speeds of thousands of kilometers per second, held in place by the immense gravity of the dark matter halo that surrounds them. The space between the galaxies is not empty, but filled with a tenuous, superheated gas called the intracluster medium, which glows faintly in X-rays and contains more mass than all the stars in all the galaxies combined. This gas is the leftover material from the formation of the cluster, the primordial hydrogen and helium that was pulled in along the filaments, but never condensed into stars. It is a reminder that most of the ordinary matter in the universe is not locked up in stars and planets, but exists in a diffuse, invisible form, detectable only through its thermal radiation and its gravitational effects. Between the filaments and nodes of the cosmic web lie the voids, vast, nearly empty regions of space that can span hundreds of millions of light years across. These are the true wildernesses of the universe, places where galaxies are rare and the density of matter is far below the cosmic average. In a typical void, you might find only a handful of small, dim galaxies, isolated and alone, separated from their nearest neighbors by distances so great that their light takes tens of millions of years to cross the gap. The voids are not completely empty, of course. They contain dark matter and some diffuse gas, but they are underdense compared to the filaments and clusters, and as a result, they expand faster than the average rate of cosmic expansion. Over time, the voids grow larger as matter is pulled out of them by the gravity of the surrounding filaments, creating an ever more pronounced contrast between the dense regions and the empty ones. If you could stand in the center of a cosmic void and look around, you would see a sky almost devoid of galaxies, with only a few faint smudges of light scattered across the darkness. It would be a profoundly lonely place, a reminder of just how empty most of the universe truly is, and how rare and precious the pockets of matter and light really are. The cosmic web owes its existence to dark matter, the mysterious substance that makes up about 85% of the matter in the universe, but does not emit, absorb, or reflect light. We cannot see dark matter directly, but we can infer its presence from its gravitational effects on visible matter. The way galaxies rotate, the way light is bent around massive clusters, and the way the cosmic web itself is structured. Dark matter does not interact with electromagnetic radiation, which means it passes through ordinary matter almost as if it were not there, detectable only through the subtle tug of gravity it exerts on everything around it. In the early universe, dark matter began to clump together under its own gravity, forming the seeds of the cosmic web. Because dark matter does not experience friction or pressure the way ordinary matter does, it could collapse into dense halos more easily, creating the gravitational wells that would later attract gas and lead to the formation of galaxies. The distribution of dark matter determines the shape of the cosmic web. Where the dark matter is densest, filaments form. Where it is sparse, voids emerge. In a very real sense, dark matter is the invisible architect of the universe, the unseen hand that guides the placement of every galaxy, every cluster, every structure we observe. The cosmic web is not a static structure, but a dynamic, evolving network shaped by the relentless pull of gravity over billions of years. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny fluctuations in density, variations of a few parts in 100,000. But these tiny fluctuations were enough. Regions that were slightly denser than average had slightly stronger gravity, and so they began to attract more matter, growing denser still. Over time, this process of gravitational amplification turned small ripples into vast structures. The densest regions collapsed first, forming the first galaxies and clusters, while the underdense regions became voids, emptying out as their matter was pulled toward the denser areas. This process continues today, with matter flowing along the filaments toward the nodes, and the voids growing ever larger and emptier. Gravity is patient and inexorable. It does not rush, but it never stops, and over the eons, it has transformed the nearly uniform early universe into the richly structured cosmos we see today. In a sense, the cosmic web is a frozen record of gravitational history, a map of how matter has moved and clustered over the lifetime of the universe. One of the most powerful tools astronomers have for understanding the cosmic web is computer simulation. By starting with the initial conditions of the early universe, the tiny density fluctuations imprinted in the cosmic microwave background. And applying the laws of gravity and gas dynamics, scientists can run simulations that evolve the universe forward in time, watching as dark matter clumps, filaments form, and galaxies emerge at the nodes. These simulations, which run on some of the most powerful supercomputers in the world, can track billions of particles over billions of years, producing virtual universes that look remarkably similar to the real one. When astronomers compare the results of these simulations to actual observations of galaxy distributions, they find an astonishing agreement, confirming that our understanding of the cosmic web is fundamentally correct. The simulations reveal details that are difficult to observe directly, such as the flow of gas along filaments, the merging of dark matter halos, and the growth of voids over time. They allow us to see the universe not as a static snapshot, but as a living, evolving system, constantly reshaping itself under the influence of gravity. And they give us a glimpse of the future, showing how the cosmic web will continue to evolve as the universe expands and ages. The filaments of the cosmic web are not made solely of dark matter. They also contain vast amounts of ordinary matter in the form of diffuse gas, known as the intergalactic medium. This gas is incredibly tenuous, with densities far lower than the best vacuum we can create on Earth. But because the filaments are so vast, the total amount of gas they contain is enormous, more than all the gas in all the galaxies combined. Most of this gas is hydrogen, left over from the Big Bang, and it exists in a variety of states, depending on its temperature and density. In the cooler regions, it is neutral or only partially ionized, and it can be detected through its absorption of light from distant quasars, creating a forest of absorption lines in the quasar's spectrum. In the hotter regions, particularly near the nodes where filaments intersect, the gas is fully ionized and heated to millions of degrees, glowing faintly in X-rays. This hot gas is a crucial component of the cosmic web, as it traces the flow of matter along the filaments and provides a reservoir of material that can eventually cool and condense to form new stars and galaxies. The intergalactic medium is also enriched with heavier elements: carbon, oxygen, silicon, iron, ejected from galaxies by supernova explosions and galactic winds, evidence that the space between galaxies is not pristine, but has been polluted by the life and death of stars. Our own Milky Way galaxy is not an isolated island, but part of a vast structure known as the Laniakea supercluster, a collection of over 100,000 galaxies spread across 520 million light-years of space. Laniakea, which means immeasurable heaven in Hawaiian, is one of the nodes of the cosmic web, a region where multiple filaments converge and galaxies are drawn together by their collective gravity. At the heart of Laniakea lies the Great Attractor, a gravitational anomaly that is pulling our galaxy and millions of others toward it at a speed of about 600 kilometers per second. We cannot see the Great Attractor directly because it lies behind the plane of the Milky Way, obscured by dust and stars, but we can measure its influence through the motions of galaxies in our cosmic neighborhood. Laniakea is not a bound structure like a galaxy cluster. It is more like a watershed, a region of space where all the galaxies are flowing in the same general direction toward the same gravitational basin. Beyond Laniakea, there are other superclusters: Shapley, Perseus, Pisces, Coma, each a node in the cosmic web, each pulling on its neighbors, creating a vast interconnected network of motion and structure that extends across the observable universe. Among the largest known structures in the cosmic web is the Sloan Great Wall, a vast filament of galaxies stretching over 1.4 billion light-years across space. Discovered in 2003 through data from the Sloan Digital Sky Survey, this immense structure contains tens of thousands of galaxies, all aligned along a single coherent filament. To put its size in perspective, light traveling at 300,000 kilometers per second would take 1.4 billion years to cross from one end of the Sloan Great Wall to the other, a distance so vast that it challenges our ability to comprehend. And yet, despite its size, the Sloan Great Wall is not unique. It is simply one of many such structures scattered throughout the universe, each a testament to the power of gravity to organize matter on the largest scales. These great walls and filaments are the bones of the cosmos, the framework upon which everything else is built. They remind us that the universe is not a chaotic, random place, but a structured, ordered system, where even the largest structures follow predictable patterns shaped by the same fundamental forces that govern the motion of planets and the fall of apples. The cosmic web is not eternal. Like everything else in the universe, it is subject to change and eventual decay. As the universe continues to expand, driven by the mysterious force known as dark energy, the filaments of the cosmic web are being stretched and thinned. The voids are growing larger, the filaments are becoming more tenuous, and the nodes are becoming more isolated from one another. In the far future, billions of years from now, the expansion of the universe will accelerate to the point where even gravitationally bound structures like galaxy clusters will begin to be torn apart. The cosmic web will dissolve, its filaments snapping, its nodes drifting apart, until eventually every galaxy is alone in an ever-expanding void, cut off from all others by the relentless stretching of space. This is the fate predicted by our current understanding of cosmology, a slow, cold dissolution of structure, a return to the uniformity that existed in the early universe, but now spread across an incomprehensibly vast and empty expanse. But that future is still trillions of years away, and for now, the cosmic web remains, a beautiful, intricate structure that connects us to the farthest reaches of the observable universe. And so, as you close your eyes and let your mind wander through the cosmic web, remember that you are part of this structure, connected to it through the gravity that holds you to the Earth to the Sun to the Milky Way, and the Milky Way to Laniakea and beyond. The atoms in your body were forged in stars that formed along the filaments of the cosmic web, and when you look up at the night sky, you are seeing the visible manifestation of an invisible architecture that spans the universe. The cosmic web is a reminder that everything is connected, that no galaxy is truly alone, and that the universe, for all its vastness, is a single, unified system. Rest now in the knowledge that you are woven into the fabric of existence, a thread in the cosmic tapestry, and let the gentle pull of gravity guide you into a deep, restorative sleep. We turn now to the greatest mystery in modern cosmology, a substance that pervades every corner of the universe, yet remains utterly invisible, detectable only through the gravitational fingerprints it leaves on everything around it. Dark matter is the silent guardian of galaxies, the invisible glue that holds cosmic structures together, and the dominant form of matter in the universe. Tonight, we will explore this enigmatic presence, tracing its influence from the rotation of spiral galaxies to the bending of light around massive clusters. And in doing so, we will come to understand that most of the universe is hidden from our eyes, existing in a realm beyond light, beyond touch, beyond all our senses except the subtle pull of gravity. The story of dark matter begins with a puzzle that emerged in the 1930s, when astronomer Fritz Zwicky was studying the Coma cluster, a massive collection of over 1,000 galaxies bound together by gravity. Zwicky measured the velocities of galaxies within the cluster and used these measurements to calculate the total mass needed to keep the cluster gravitationally bound. What he found was shocking. The galaxies were moving so fast that based on the visible matter alone, they should have escaped the cluster's gravity long ago, scattering into the void. Yet the cluster remained intact, which meant there had to be far more mass present than could be accounted for by the stars and gas he could observe. Zwicky called this unseen mass dunkel materie, dark matter, and estimated that it outweighed the visible matter by a factor of about 400 to 1. His discovery was largely ignored for decades, dismissed as an anomaly or a measurement error, but it planted the seed of an idea that would eventually revolutionize our understanding of the cosmos. The universe, it seemed, was hiding most of its mass in plain sight, or rather, in plain darkness. The most compelling evidence for dark matter came in the 1970s, when astronomer Vera Rubin and her colleagues measured the rotation curves of spiral galaxies, graphs showing how fast stars and gas orbit around the galactic center at different distances. According to Newton's laws of gravity, stars farther from the center should orbit more slowly, just as the outer planets in our solar system orbit the sun more slowly than the inner planets. But when Rubin measured the rotation speeds of stars in galaxies like Andromeda, she found something completely unexpected. The stars at the outer edges of the galaxy were moving just as fast as those closer to the center, and in some cases, even faster. This flat rotation curve defied all expectations based on the visible matter distribution. The only way to explain it was to assume that galaxies are embedded in vast halos of invisible matter, extending far beyond the visible disk, whose gravity keeps the outer stars moving at high speeds. These dark matter halos are enormous, often 10 times larger than the visible galaxy, and they contain several times more mass than all the stars, gas, and dust combined. Rubin's work provided the smoking gun for dark matter, transforming it from a fringe hypothesis into a cornerstone of modern astrophysics. One of the most beautiful confirmations of dark matter comes from gravitational lensing, a phenomenon predicted by Einstein's general theory of relativity. According to Einstein, mass warps the fabric of space-time, and light traveling through this warped space follows curved paths, much like a marble rolling across a stretched rubber sheet. When light from a distant galaxy passes near a massive object like a galaxy cluster, the cluster's gravity bends the light, distorting and magnifying the image of the background galaxy. By studying these distortions, astronomers can map the distribution of mass in the foreground cluster, including both visible and invisible matter. What they find is remarkable. The mass distribution inferred from gravitational lensing far exceeds the mass of the visible galaxies and gas, and the shape of the mass distribution matches the predictions for dark matter halos. In some cases, such as the famous bullet cluster, gravitational lensing has revealed dark matter and ordinary matter separated from each other, providing direct evidence that dark matter is a distinct substance, not simply a modification of gravity. The lensing maps show dark matter as a ghostly presence, invisible to our telescopes but unmistakably real, shaping the paths of light across the cosmos. Before we can understand what dark matter might be, it helps to understand what it is not. Dark matter is not ordinary matter that happens to be dark. It is not planets, asteroids, black holes, or clouds of cold gas. We know this because ordinary matter, also called baryonic matter, is made of protons and neutrons, and the total amount of baryonic matter in the universe is tightly constrained by observations of Big Bang nucleosynthesis and the cosmic microwave background. These observations tell us that baryonic matter makes up only about 5% of the total mass energy of the universe, far too little to account for the dark matter we observe. Dark matter is also not antimatter, because antimatter annihilates with matter, producing gamma rays, and we do not see the telltale signature of such annihilations on the scales required. It is not black holes or other compact objects, because surveys searching for gravitational microlensing events have ruled out large populations of such objects in the mass range that would be needed. Dark matter is something fundamentally different, a new form of matter that does not interact with light or ordinary matter except through gravity, existing in a shadow realm that overlaps with our own, but remains forever out of reach of our senses. The most popular hypothesis for the nature of dark matter is that it consists of weakly interacting massive particles, or WIMPs. These hypothetical particles would have masses tens to hundreds of times greater than a proton, and they would interact with ordinary matter only through gravity and the weak nuclear force, one of the four fundamental forces of nature. The weak force is responsible for certain types of radioactive decay and operates only over extremely short distances, which means WIMPs would pass through ordinary matter almost as if it were not there, only very rarely colliding with an atomic nucleus. This makes WIMPs incredibly difficult to detect, but not impossible. Physicists have built sensitive detectors deep underground, shielded from cosmic rays and other background radiation, in the hope of catching a rare WIMP collision. So far, despite decades of searching, no definitive detection has been made. But the search continues, driven by the tantalizing possibility that we might one day capture a particle of dark matter and study its properties directly. WIMPs are attractive not only because they fit the observational evidence, but also because they arise naturally in certain extensions of the standard model of particle physics, such as supersymmetry, which predicts a whole zoo of new particles, some of which could be stable and massive enough to be dark matter. While WIMPs are the leading candidate, they are not the only possibility. Another intriguing option is the axion, a hypothetical particle that was originally proposed to solve a different problem in particle physics, but which could also serve as dark matter. Axions would be much lighter than WIMPs, with masses billions of times smaller than an electron, but they would be produced in such vast quantities in the early universe that their collective mass could account for all the dark matter we observe. Because they are so light, axions would behave more like waves than particles, forming a diffuse, coherent field that permeates the galaxy. Detecting axions requires a different approach than detecting WIMPs. Instead of looking for collisions, physicists search for the faint electromagnetic signals that axions would produce when passing through strong magnetic fields. Other candidates include sterile neutrinos, primordial black holes formed in the first moments after the Big Bang, and even more exotic possibilities like dark photons or self-interacting dark matter. The truth is, we do not yet know what dark matter is made of, and it is possible that the answer will surprise us, revealing new physics beyond our current theories and opening up entirely new realms of understanding. Every galaxy, from the smallest dwarf to the largest elliptical, is embedded in a dark matter halo, a roughly spherical cloud of dark matter that extends far beyond the visible stars and gas. These halos are the scaffolding upon which galaxies are built, providing the gravitational framework that allows ordinary matter to collapse and form stars. In the early universe, dark matter began to clump together under its own gravity, forming the first halos long before the first stars ignited. Ordinary matter, in the form of hydrogen and helium gas, fell into these gravitational wells, where it cooled, condensed, and eventually formed the first galaxies. Without dark matter, galaxies as we know them could not exist. The ordinary matter would not have enough gravity to hold itself together, and it would be dispersed by the expansion of the universe. The halos are not uniform. They have structure, with denser regions near the center and more diffuse regions at the edges, and they are filled with substructure, smaller clumps and streams of dark matter left over from the mergers and interactions of smaller halos over cosmic time. This substructure is a prediction of the cold dark matter model, and detecting it is one of the key tests of our understanding of dark matter's nature. Perhaps the most dramatic evidence for dark matter comes from the Bullet Cluster, a pair of galaxy clusters that collided with each other at high speed about 150 million years ago. When the clusters collided, the galaxies passed through each other largely unscathed, because the distances between stars are so vast that direct collisions are rare. But the hot gas that fills the space between galaxies did collide, creating a shockwave and slowing down due to friction. Gravitational lensing observations of the Bullet Cluster reveal that the majority of the mass is not located where the gas is, but rather where the galaxies are, offset from the gas by a significant distance. This separation of mass and gas is exactly what we would expect if dark matter exists. The dark matter halos, which do not experience friction, passed through each other and continued on, while the ordinary matter in the form of gas was slowed and left behind. The Bullet Cluster provides a clear visual demonstration that dark matter is real and distinct from ordinary matter, and it has become one of the most iconic images in the case for dark matter's existence. Dark matter is not just a passive presence. It plays an active role in shaping the formation and evolution of galaxies. In the early universe, tiny fluctuations in the density of dark matter were amplified by gravity, growing into the first dark matter halos. These halos acted as seeds, attracting ordinary matter and triggering the formation of the first stars and galaxies. As time went on, smaller halos merged to form larger ones, and galaxies grew through a combination of mergers and the accretion of gas from the surrounding intergalactic medium. The properties of a galaxy, its size, shape, rotation speed, and star formation rate are all influenced by the mass and structure of its dark matter halo. Simulations show that the hierarchical assembly of dark matter halos, with small halos merging to form larger ones over billions of years, naturally produces the diversity of galaxy types we observe, from small, irregular dwarfs to massive, elliptical giants. Dark matter also regulates the rate at which gas can cool and form stars, because the depth of the gravitational well determines how much energy the gas must radiate away before it can collapse. In this way, dark matter is intimately connected to the story of galaxy formation, a silent partner in the cosmic dance of structure and light. Just as galaxies are embedded in dark matter halos, the cosmic web itself is primarily a structure of dark matter. The filaments that connect galaxy clusters, the nodes where clusters form, and the voids that separate them are all defined by the distribution of dark matter. Ordinary matter follows the gravitational pull of dark matter, flowing along the filaments and accumulating at the nodes. But it is dark matter that sets the stage. In fact, the cosmic web would exist even if there were no ordinary matter at all. It is a purely gravitational structure, shaped by the collapse and merging of dark matter halos over cosmic time. The dark matter web is invisible to our telescopes, but we can infer its presence from the distribution of galaxies and the patterns of gravitational lensing. It is the hidden architecture of the universe. the framework that supports everything we can see, and it reminds us that the visible universe is just the tip of the iceberg, a thin veneer of light and matter, overlaying a vast, dark foundation. Despite decades of research and countless observations, dark matter remains one of the deepest mysteries in science. We know it exists, we know how much of it there is, and we know how it behaves, but we do not know what it is made of. Every galaxy, every cluster, every structure in the universe bears the imprint of dark matter's presence, and yet it eludes all our attempts to capture it directly. Perhaps one day, a detector deep underground will record the faint signal of a dark matter particle colliding with an atomic nucleus, or a particle accelerator will produce dark matter in the laboratory, or a new theoretical insight will reveal its nature in a way we have not yet imagined. Until then, dark matter remains a silent guardian, an invisible presence that shapes the cosmos, holding galaxies together and guiding the flow of matter across the universe. As you drift towards sleep, let yourself rest in this mystery, in the knowledge that the universe is far stranger and more wonderful than we can see, and that the darkness is not empty, but filled with a presence we are only beginning to understand. We arrive now at the deepest enigma of all, a force so pervasive that it fills every cubic centimeter of space, yet so subtle that it went undetected for most of human history. Dark energy is the invisible breath that inflates the universe, the mysterious pressure that drives galaxies apart and accelerates the expansion of space itself. It constitutes nearly 70% of the total mass energy of the cosmos, dwarfing both ordinary matter and dark matter, and yet we know almost nothing about its true nature. Tonight, we will explore this cosmic mystery, tracing the discovery of the accelerating universe and contemplating the profound implications of a force that will ultimately determine the fate of everything that exists. The story of dark energy begins in the 1920s, when astronomer Edwin Hubble made one of the most important discoveries in the history of science. The universe is expanding. By measuring the distances to distant galaxies and comparing them to the velocities at which those galaxies were moving away from us, Hubble found a clear relationship. The farther away a galaxy was, the faster it was receding. This relationship, now known as Hubble's law, revealed that space itself is expanding, carrying galaxies along with it like raisins in a rising loaf of bread. The implications were staggering. If the universe is expanding now, it must have been smaller in the past, and if you run the clock backward far enough, you arrive at a moment when all of space was compressed into an infinitesimally small point, the Big Bang. For decades after Hubble's discovery, astronomers assumed that the expansion of the universe must be slowing down over time, because the gravitational attraction between galaxies should act as a brake, gradually decelerating the expansion. It seemed obvious that gravity, the force that holds planets in orbit and binds galaxies together, would eventually halt the expansion, and perhaps even reverse it, causing the universe to collapse back in on itself in a big crunch. But the universe, as it so often does, had other plans. In the late 1990s, two independent teams of astronomers set out to measure the deceleration of the universe by observing distant supernovae, exploding stars that serve as cosmic distance markers. Type Ia supernovae are particularly useful for this purpose, because they have a consistent peak brightness, allowing astronomers to determine their distance by measuring how bright they appear from Earth. By comparing the distances to these supernovae with their redshifts, the amount by which their light has been stretched by the expansion of space, the teams hoped to measure how much the expansion had slowed over billions of years. What they found was completely unexpected. The distant supernovae were fainter than they should be, which meant they were farther away than predicted. The universe was not decelerating, it was accelerating. The expansion of space was speeding up, driven by some unknown force that was pushing galaxies apart with ever-increasing vigor. This discovery, announced in 1998, sent shockwaves through the scientific community and earned the leaders of the two teams the Nobel Prize in Physics in 2011. It meant that the universe was dominated not by matter, but by a mysterious form of energy that exerts a negative pressure, a repulsive force that counteracts gravity and drives the acceleration. Ironically, the concept of a repulsive force in the universe was not new. It had been proposed and then abandoned by Albert Einstein himself. When Einstein first applied his general theory of relativity to cosmology in 1917, he found that his equations predicted a dynamic universe, one that would either expand or contract over time. But at the time, the prevailing belief was that the universe was static and eternal. So Einstein added a term to his equations called the cosmological constant, represented by the Greek letter lambda, la. This constant acted as a repulsive force that exactly balanced the attractive force of gravity, allowing for a static universe. When Hubble discovered that the universe was expanding, Einstein realized that the cosmological constant was unnecessary and famously called it his biggest blunder. But with the discovery of the accelerating universe, the cosmological constant was resurrected. If you interpret lambda as a form of energy inherent to space itself, a constant energy density that does not dilute as the universe expands, it produces exactly the kind of repulsive force needed to explain the acceleration. This energy, now called dark energy, would be a fundamental property of the vacuum, a kind of baseline energy that permeates all of space and exerts a negative pressure, pushing space apart. The simplest explanation for dark energy is that it is vacuum energy, the energy of empty space itself. According to quantum field theory, even a perfect vacuum is not truly empty. It is filled with virtual particles that constantly pop in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating and returning that energy. These quantum fluctuations give the vacuum a non-zero energy density, and if this energy density is positive and constant, it would act exactly like Einstein's cosmological constant, exerting a repulsive force that drives the expansion of the universe. The problem is that when physicists try to calculate the expected value of vacuum energy from quantum field theory, they get a number that is absurdly large, about 120 orders of magnitude larger than the observed value of dark energy. This is one of the worst predictions in the history of physics, a discrepancy so vast that it suggests we are missing something fundamental in our understanding of quantum mechanics. Gravity, or both. Despite this mismatch, vacuum energy remains the leading candidate for dark energy because it naturally produces a constant energy density that does not change over time, which is consistent with observations. Not all physicists are convinced that dark energy is simply a cosmological constant. An alternative idea is that dark energy is a dynamic field, similar to the fields that give rise to fundamental forces and particles, but with properties that allow it to drive the acceleration of the universe. This hypothetical field is called quintessence, a name derived from the ancient Greek concept of the fifth element. Unlike the cosmological constant, which has a fixed energy density, quintessence would have an energy density that can change over time and vary from place to place. This would mean that the acceleration of the universe might not be constant, but could speed up or slow down as the quintessence field evolves. Detecting such changes would require extremely precise measurements of the expansion history of the universe, and so far, observations are consistent with a constant dark energy, but they do not rule out quintessence entirely. Other, more exotic theories propose modifications to general relativity itself, suggesting that gravity behaves differently on cosmic scales than it does in the solar system, and that what we interpret as dark energy is actually a sign that our theory of gravity is incomplete. These ideas remain speculative, but they highlight the fact that dark energy is one of the greatest unsolved problems in physics. The history of the universe can be understood as a cosmic tug-of-war between matter and dark energy. In the early universe, matter dominated, and its gravitational pull slowed the expansion, though it was never strong enough to halt it completely. As the universe expanded, the density of matter decreased. There was more space for the same amount of matter. But the density of dark energy, if it is indeed a cosmological constant, remained the same. Eventually, about 5 billion years ago, dark energy overtook matter as the dominant component of the universe's energy budget. And from that point on, the expansion began to accelerate. Before this transition, the universe was decelerating, and structures like galaxies and clusters could still form as gravity pulled matter together. But once dark energy took over, the acceleration began to inhibit the formation of new large-scale structures, because the expansion of space started to overcome the gravitational attraction on the largest scales. Today, dark energy makes up about 68% of the total energy of the universe, dark matter about 27%, and ordinary matter just 5%. This means that the vast majority of the universe is composed of things we do not understand, and the future evolution of the cosmos will be determined almost entirely by the properties of dark energy. One of the key tools for studying dark energy is the measurement of cosmic expansion through redshift. When light from a distant galaxy travels through expanding space, its wavelength is stretched, shifting it toward the red end of the spectrum. The amount of redshift is directly related to how much the universe has expanded since the light was emitted. And by measuring the redshifts of galaxies at different distances, astronomers can reconstruct the expansion history of the universe. The current rate of expansion is quantified by the Hubble constant, which tells us how fast galaxies are receding per unit of distance. Measuring the Hubble constant with high precision has been a major goal of cosmology, but it has also led to a puzzle known as the Hubble tension. Different methods of measuring the Hubble constant give slightly different values, with measurements based on the cosmic microwave background, yielding a lower value than measurements based on nearby supernovae and other distance indicators. This discrepancy could be a sign of systematic errors in the measurements, or it could hint at new physics, such as a change in the properties of dark energy over time. Resolving the Hubble tension is one of the most pressing challenges in cosmology today. The discovery of dark energy has profound implications for the ultimate fate of the universe. If dark energy remains constant, as current observations suggest, then the universe will continue to expand forever, and the expansion will continue to accelerate. Over billions of years, galaxies outside our local group will be carried away by the expansion of space, receding faster and faster until they cross the cosmic horizon, the boundary beyond which light can no longer reach us. Eventually, the observable universe will shrink, containing only the Milky Way and the few dozen galaxies gravitationally bound to it in the local group. The rest of the cosmos will disappear from view, their light stretched to infinite wavelengths by the relentless expansion. Stars will continue to form and die, but the supply of gas will eventually run out, and the universe will grow darker and colder. Trillions of years from now, the last stars will flicker out, leaving behind a cosmos filled with black holes, dead stars, and the faint glow of Hawking radiation. This is the scenario known as the Big Freeze, or heat death, a slow, cold fade into darkness, driven by the inexorable push of dark energy. If dark energy is not constant but instead grows stronger over time, a possibility allowed by some quintessence models, the fate of the universe could be even more dramatic. In this scenario, known as the Big Rip, the acceleration of the universe would increase without limit, eventually becoming so strong that it would overcome not just the gravitational binding of galaxy clusters, but also the gravity holding galaxies together, the gravity binding stars to planets, and even the electromagnetic and nuclear forces holding atoms and nuclei together. First, galaxy clusters would be torn apart, then galaxies, then solar systems, then planets, then molecules, then atoms, and finally, in the last fraction of a second before the end, even atomic nuclei would be ripped apart, and space itself would be torn asunder in a cataclysmic finale. The Big Rip is a speculative scenario, and current observations do not favor it, but it remains a theoretical possibility, a reminder that the nature of dark energy is still deeply uncertain, and that the future of the universe hangs on the properties of a force we barely understand. Some physicists have speculated that the value of dark energy, the cosmological constant, might be related to the concept of the multiverse, the idea that our universe is just one of many, each with different physical laws and constants. In this view, the cosmological constant is not determined by fundamental physics, but is instead a random environmental parameter that varies from universe to universe. Most values of the cosmological constant would be incompatible with the formation of galaxies and stars, and hence with the existence of life. But in a multiverse, we would naturally find ourselves in one of the rare universes where the cosmological constant is small enough to allow structures to form. This is an example of the anthropic principle, the idea that the properties of the universe are constrained by the requirement that it must be capable of supporting observers. The multiverse hypothesis is controversial and difficult to test, but it offers one possible explanation for why the cosmological constant has the value it does, rather than being zero or enormously large. Dark energy remains one of the most profound mysteries in all of science. We have measured its effects with great precision. We know how much of it there is, and we know how it influences the expansion of the universe, but we do not know what it is or why it exists. It is a force that fills the universe, yet leaves no trace except in the motion of galaxies across billions of light years. It is the dominant component of the cosmos, yet it is invisible, intangible, and utterly unlike anything we have encountered in our laboratories. As you close your eyes and let your thoughts drift into the vastness of space, imagine the universe breathing, expanding with each exhalation, driven by the invisible pressure of dark energy. Feel the gentle push that separates galaxies, the slow, inexorable force that will shape the cosmos for all eternity. Rest in the knowledge that the universe is still unfolding, still revealing its secrets, and that the darkness is not empty, but filled with a presence we are only beginning to comprehend. Sleep now, and let the infinite breath of the cosmos carry you into dreams. We venture now into the realm of cosmic geometry, where the very shape of space itself becomes a question to be answered, a mystery to be unraveled through careful observation and mathematical reasoning. Is the universe flat, like an infinite plane, or curved like the surface of a sphere, or perhaps saddle-shaped, curving in opposite directions? The answer to this question determines not only the ultimate fate of the cosmos, but also the very nature of infinity itself. Tonight, we will explore how astronomers measure the curvature of space, how the geometry of the universe is encoded in the patterns of ancient light, and how the cosmos reveals itself to be balanced on a knife's edge between different possible geometries, each with its own profound implications. When we speak of the shape of the universe, we are not talking about its shape in the ordinary sense, like the shape of a ball or a box. We are talking about the intrinsic geometry of space itself, whether parallel lines remain parallel forever, whether the angles of a triangle add up to exactly 180 degrees, whether space extends infinitely or curves back on itself. Einstein's general theory of relativity tells us that space is not a fixed, unchanging stage on which events unfold, but a dynamic entity that can be warped and curved by the presence of matter and energy on small scales, like the solar system. This curvature is subtle, causing planets to orbit the sun and light to bend around massive objects. But on cosmic scales, the curvature of space becomes a global property, determined by the total density of matter and energy in the universe. If the density is exactly equal to a critical value, space is flat, extending infinitely in all directions with the familiar geometry of Euclidean space. If the density is greater than the critical value, space is positively curved, like the surface of a sphere, and the universe is finite in size, though it has no boundary or edge. If the density is less than the critical value, space is negatively curved, like a saddle, and the universe is infinite, with parallel lines diverging as they extend into the distance. The most precise measurements of cosmic curvature come from observations of the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. This ancient light, released when the universe was just 380,000 years old, carries within it a detailed map of the density fluctuations in the early universe. Tiny variations in temperature that correspond to regions that were slightly denser or less dense than average. These fluctuations appear as a pattern of hot and cold spots on the sky, and the size of these spots is directly related to the geometry of space. In a flat universe, the spots have a characteristic angular size determined by the distance light could travel in the early universe, and the distance from us to the surface of last scattering. In a positively curved universe, the spots appear larger because light rays converge as they travel through curved space, magnifying distant objects. In a negatively curved universe, the spots appear smaller because light rays diverge. By measuring the angular size of the fluctuations with exquisite precision, satellites like WMP and Planck have determined that the universe is flat to within a fraction of a percent, with a total density almost exactly equal to the critical density. The critical density is a fundamental quantity in cosmology, representing the dividing line between different cosmic geometries. It depends on the current expansion rate of the universe, quantified by the Hubble constant, and it has a value of about 10 circumflex 29 grams per cubic centimeter, roughly equivalent to a few hydrogen atoms per cubic meter of space. Cosmologists often express the density of the universe in terms of a parameter called omega, which is the ratio of the actual density to the critical density. If omega equals 1, the universe is flat. If omega is greater than 1, the universe is positively curved and finite. If omega is less than 1, the universe is negatively curved and infinite. Observations of the cosmic microwave background, combined with measurements of the distribution of galaxies and the expansion history of the universe, all point to the same conclusion. Omega is very close to 1, meaning the universe is very close to being perfectly flat. This raises a profound question. Why is the universe so finely tuned to be flat? In the early universe, Even a tiny deviation from flatness would have been amplified over time, leading to a universe that is either strongly curved or that collapsed back on itself long ago. The fact that the universe is still so close to flat today suggests that it was extraordinarily flat in the beginning, a puzzle that is addressed by the theory of cosmic inflation. Cosmic inflation, the brief period of exponential expansion in the first fraction of a second after the Big Bang, provides an elegant solution to the flatness problem. During inflation, the universe expanded by a factor of at least 10 circumflex 26, stretching any initial curvature to such enormous scales that the observable universe appears flat, just as the surface of a balloon appears flat when you zoom in on a tiny patch. Imagine taking a curved surface, like the skin of an orange, and inflating it to the size of the Earth. The curvature would become so slight that any small region would appear perfectly flat. Inflation does the same thing to the universe, taking whatever curvature existed initially and diluting it to the point where it is undetectable within the observable universe. This means that the universe could still have a global curvature. It could be a vast, positively curved hypersphere, for example. But the curvature would be so gentle that we cannot measure it with current technology. The observable universe would be just a tiny patch on this hypersphere, too small to reveal the overall curvature. Inflation also explains why the cosmic microwave background is so uniform. Regions that are now on opposite sides of the sky were once close together in causal contact before inflation stretched them apart. Even if the universe is flat in terms of its curvature, it could still have an interesting topology. The way space is connected on the largest scales, a flat universe could be infinite, extending forever in all directions. Or it could be finite but unbounded, like a torus or a three-dimensional version of a video game screen, where traveling far enough in one direction brings you back to where you started. In a toroidal universe, for example, space would be flat locally, but globally it would wrap around on itself, so that if you could travel far enough in a straight line, you would eventually return to your starting point. Astronomers have searched for evidence of such topology by looking for repeating patterns in the cosmic microwave background. If the universe wraps around, we might see the same features appearing in multiple locations on the sky, like seeing multiple images of the same object in a hall of mirrors. So far, no such patterns have been found, which suggests that if the universe does have a non-trivial topology, it is larger than the observable universe, and we are confined to a region too small to detect the wrapping. The question of cosmic topology remains open, a tantalizing mystery that hints at the possibility of a universe far stranger than we can currently observe. It is important to distinguish between the observable universe and the entire universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang, a sphere roughly 93 billion light-years in diameter, centered on Earth. This is not the entire universe, but merely the portion we can see. The entire universe could be much larger, perhaps infinite, but we can never observe regions beyond the cosmic horizon, because light from those regions has not yet had time to reach us, and in an accelerating universe, it never will. The geometry we measure, the flatness of space, applies to the observable universe, but we cannot say with certainty what the geometry of the entire universe is. It could be that the universe is flat everywhere, extending infinitely. Or it could be that the observable universe is just a tiny flat patch on a much larger, curved manifold. This is one of the humbling lessons of cosmology. There are limits to what we can know, boundaries beyond which observation cannot reach, and the true nature of the cosmos may forever remain partially hidden from us. In a flat universe, Parallel lines remain parallel forever, extending to infinity without ever meeting or diverging. This is the geometry of Euclidean space, the geometry we learn in school, where the angles of a triangle add up to 180 degrees and the circumference of a circle is exactly 2 pi times its radius. It is a geometry of infinite extent, where there is always more space beyond any boundary you can imagine, where you can travel forever in a straight line and never return to where you started. In a positively curved universe, parallel lines eventually converge, meeting at a point like lines of longitude on a globe. In such a universe, the angles of a triangle add up to more than 180 degrees, and the universe is finite in volume, though it has no edge, just as the surface of a sphere is finite but has no boundary. In a negatively curved universe, parallel lines diverge, spreading apart as they extend into the distance, and the angles of a triangle add up to less than 180 degrees. Such a universe is infinite, but with a geometry that is fundamentally different from flat space, a hyperbolic geometry where space expands faster in some directions than others. The fact that our universe appears to be flat means that we live in a cosmos where infinity is simple and straightforward, where space extends without limit in all directions, governed by the familiar rules of Euclidean geometry. One of the puzzles that inflation solves is the horizon problem, which arises from the fact that the cosmic microwave background is remarkably uniform across the entire sky, with a temperature that varies by only a few parts in 100,000. This uniformity is puzzling because in the standard Big Bang model without inflation, regions on opposite sides of the sky were never in causal contact. They were too far apart for light to have traveled between them in the time since the Big Bang. So how did they end up at the same temperature? Inflation provides the answer. Before inflation, the entire observable universe was a tiny region, small enough that all parts of it were in causal contact and could reach thermal equilibrium. Then inflation stretched this tiny uniform region to enormous scales, creating the uniformity we observe today. The horizon problem is intimately connected to the geometry of the universe, because the size of the causal horizon, the distance light can travel in a given time, depends on the expansion history and the curvature of space. By solving the horizon problem, inflation also naturally produces a flat universe, because the exponential expansion flattens any initial curvature. In a curved universe, measuring distances becomes more complicated than simply multiplying the speed of light by the time it takes for light to travel. The expansion of space means that distances are constantly changing, and the curvature of space affects how we interpret the light we receive from distant objects. Cosmologists use several different definitions of distance, each appropriate for different purposes. The co-moving distance is the distance to an object measured in a coordinate system that expands with the universe, so that the co-moving distance to a distant galaxy remains constant even as the universe expands. The luminosity distance is the distance inferred from how bright an object appears, taking into account the dimming of light due to the expansion of space. The angular diameter distance is the distance inferred from the apparent size of an object, taking into account the way curvature affects the angles at which we see distant objects. In a flat universe, these distances are related in simple ways, but in a curved universe, the relationships become more complex, and measuring them allows astronomers to probe the geometry of space. The fact that all these distance measurements are consistent with a flat universe is one of the strongest pieces of evidence for the flatness of space. Imagine drawing a triangle on the largest possible scale, with vertices separated by billions of light years, using the paths of light rays as the sides. In a flat universe, the angles of this cosmic triangle would add up to exactly 180 degrees, just as they do for a triangle drawn on a flat piece of paper. In a positively curved universe, the angles would add up to more than 180 degrees, because the curvature of space causes the sides of the triangle to bow outward, like a triangle drawn on the surface of a sphere. In a negatively curved universe, the angles would add up to less than 180 degrees, because the sides bow inward, like a triangle drawn on a saddle. By measuring the angles of such a triangle, using, for example, the cosmic microwave background and the distribution of galaxies, astronomers can determine the curvature of space. The measurements show that the angles add up to 180 degrees, within the limits of observational precision, confirming that the universe is flat. This cosmic triangle is not just a thought experiment. It is a real measurement encoded in the patterns of light and matter that fill the universe. As you drift towards sleep, let your mind wander through the infinite expanse of a flat universe, where space extends forever in all directions, where parallel lines never meet, where there is always more to explore, beyond any horizon. The geometry of the universe is a profound truth, a fundamental property of existence that shapes the destiny of everything within it. The fact that the universe is flat means that it is infinite, or at least so vast that its curvature is undetectable, and that it will expand forever, growing colder and darker as the eons pass. But for now, in this moment, the universe is filled with light and structure, with galaxies and stars and planets, all existing within the simple, elegant geometry of flat space. Rest in the knowledge that the cosmos is comprehensible, that its shape can be measured and understood, and that the same mathematical laws that govern the fall of an apple also govern the curvature of space across billions of light years. Sleep now and dream of infinity, of a universe without boundaries, stretching endlessly into the eternal night. We arrive now at one of the most remarkable discoveries in the history of cosmology, a faint whisper of light that has been traveling through space for nearly 14 billion years, carrying with it the imprint of the universe as it was in its infancy. The cosmic microwave background is the oldest light we can observe, the afterglow of the Big Bang itself, and within its subtle patterns lies a treasure trove of information about the origin, composition, and fate of the cosmos. Tonight, we will explore this ancient radiation, tracing its journey from the moment of recombination to the present day, and discovering how it has become the most powerful tool we have for understanding the universe on the largest scales. The cosmic microwave background was discovered by accident in 1964 by two radio astronomers, Arno Penzias and Robert Wilson, who were working at Bell Telephone Laboratories in New Jersey. They were using a large horn antenna to study radio signals from the Milky Way, but they kept detecting a persistent background noise that seemed to come from all directions in the sky, regardless of where they pointed the antenna. At first, they thought it was interference from nearby cities, or perhaps the result of pigeon droppings that had accumulated inside the antenna. But even after cleaning the antenna thoroughly, the signal remained. It was uniform, unchanging, and present at all times of day and night, with a temperature of about 3 degrees above absolute zero. Unbeknownst to Penzias and Wilson, physicists at nearby Princeton University had been predicting the existence of just such a signal. A relic radiation left over from the Big Bang, cooled by the expansion of the universe to a faint microwave glow. When the two groups learned of each other's work, they realized that Penzias and Wilson had stumbled upon one of the most important discoveries in cosmology. The cosmic microwave background was the smoking gun for the Big Bang theory, direct evidence that the universe had once been in a hot, dense state. And it earned Penzias and Wilson the Nobel Prize in Physics in 1978. The cosmic microwave background originates from a moment in cosmic history known as recombination, which occurred about 380,000 years after the Big Bang. Before this time, the universe was a hot, dense plasma filled with free electrons and atomic nuclei, and photons could not travel far before being scattered by an electron. The universe was opaque, like a thick fog, and light was trapped in an endless cycle of absorption and re-emission. But as the universe expanded and cooled, the temperature dropped to the point where electrons could combine with nuclei to form neutral atoms, primarily hydrogen and helium. With the electrons bound into atoms, photons were suddenly free to travel through space without being scattered, and the universe became transparent. The light that was released at this moment, the moment of recombination, has been traveling through space ever since, and it is this light that we observe today as the cosmic microwave background. The surface of last scattering is the spherical shell in space from which this light originates, located about 46 billion light-years away in all directions, marking the boundary of the observable universe. When we observe the cosmic microwave background, we are looking back in time to the universe as it was just 380,000 years old, seeing the glow of the primordial plasma as it cooled and became transparent. One of the most striking features of the cosmic microwave background is its spectrum, the distribution of its energy across different wavelengths. The CMB has an almost perfect black-body spectrum, the characteristic spectrum of radiation emitted by an object in thermal equilibrium, with a temperature of 2.725 Kelvin. This is exactly what we would expect from the hot, dense plasma of the early universe, which was in thermal equilibrium before recombination. The fact that the CMB has such a perfect black body spectrum is powerful evidence that the universe was once in a state of thermal equilibrium, and it rules out alternative explanations for the CMB, such as the idea that it might be produced by a collection of distant stars or galaxies. The spectrum was measured with exquisite precision by the COBE satellite in 1990, and the results matched the theoretical predictions so closely that they were described as the most perfect blackbody spectrum ever measured. This precision is a testament to the power of the Big Bang theory and the accuracy of our understanding of the early universe. While the cosmic microwave background is remarkably uniform, with a temperature that varies by only a few parts in 100,000 across the sky, it is not perfectly smooth. Embedded in the CMB are tiny fluctuations, regions that are slightly hotter or colder than the average, and these fluctuations are the seeds of all the structure we see in the universe today. The hot spots correspond to regions that were slightly denser than average in the early universe, and the cold spots correspond to regions that were slightly less dense. Over billions of years, gravity amplified these tiny density differences, causing the denser regions to collapse and form galaxies, stars, and planets, while the less dense regions became the cosmic voids. The fluctuations in the CMB are a snapshot of the universe at the moment of recombination, a map of the initial conditions that set the stage for the formation of all cosmic structure. By studying the pattern of these fluctuations, their size, shape, and distribution, astronomers can learn about the composition of the universe, the nature of dark matter and dark energy, and the processes that occurred in the first moments after the Big Bang. The fluctuations in the cosmic microwave background are not random. They have a characteristic pattern that reflects the physics of the early universe. Before recombination, the universe was filled with a plasma of photons, electrons, and atomic nuclei. and this plasma behaved like a fluid, with pressure and density variations that could support sound waves. Regions that were denser than average had higher pressure, and this pressure caused them to expand, creating waves that propagated through the plasma. These are called baryon acoustic oscillations, and they left an imprint on the distribution of matter in the early universe. When recombination occurred and the photons decoupled from the matter, the oscillations were frozen in place, and they appear today as a characteristic pattern in the CMB fluctuations, a series of peaks and troughs in the power spectrum that correspond to different scales of oscillation. The first peak corresponds to regions that had just reached maximum compression at the moment of recombination. The second peak to regions that had just reached maximum rarefaction, and so on. By measuring the positions and heights of these peaks, cosmologists can determine the density of ordinary matter, dark matter, and dark energy, the curvature of space, and the rate of expansion of the universe, all with remarkable precision. The largest variation in the cosmic microwave background is not due to the structure of the early universe, but to our own motion through space, because the Earth, the Sun, and the Milky Way are all moving relative to the rest frame defined by the CMB. The radiation appears slightly hotter in the direction we are moving toward, and slightly cooler in the direction we are moving away from. This is called the dipole anisotropy, and it is a result of the Doppler effect, the same effect that causes the pitch of a siren to change as an ambulance drives past. By measuring the dipole anisotropy, astronomers have determined that the solar system is moving at a speed of about 370 kilometers per second, relative to the CMB, in the direction of the constellation Leo. This motion is the result of the gravitational pull of nearby structures, including the Virgo cluster and the Great Attractor, and it provides a cosmic reference frame against which all other motions can be measured. The dipole anisotropy is a reminder that we are not at rest in the universe, but a part of a vast dynamic system, constantly in motion under the influence of gravity. In addition to temperature fluctuations, the cosmic microwave background also has a subtle polarization pattern, a preferential orientation of the electric field of the light waves. This polarization arises from the scattering of photons by electrons at the moment of recombination, and it carries additional information about the conditions in the early universe. There are two types of polarization in the CMB. E-mode polarization, which is produced by density fluctuations and is relatively easy to detect, and B-mode polarization, which can be produced by gravitational waves from the inflationary epoch or by the gravitational lensing of E-mode polarization by intervening structures. The detection of primordial B-mode polarization would be a major discovery, providing direct evidence for cosmic inflation and opening a window into the physics of the very early universe, when energies were far higher than anything we can achieve in particle accelerators. So far, B-mode polarization from gravitational lensing has been detected, but the primordial signal from inflation remains elusive, hidden beneath foreground contamination from our own galaxy and the faintness of the signal itself. Our understanding of the cosmic microwave background has been revolutionized by a series of space missions designed to map the CMB with ever-increasing precision. The first was COBE, the Cosmic Background Explorer, launched in 1989, which confirmed the black-body spectrum of the CMB and made the first detection of the temperature fluctuations, earning its principal investigators the Nobel Prize in Physics in 2006. COBE was followed by WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, which produced detailed maps of the CMB fluctuations and measured the age, composition, and geometry of the universe with unprecedented accuracy. WMAP's results confirmed the standard model of cosmology, showing that the universe is flat, composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy, and is 13.8 billion years old. The most recent mission is Planck, launched in 2009, which mapped the CMB with even higher resolution and sensitivity, refining the measurements of cosmological parameters and searching for subtle signals, such as primordial B-mode polarization. Together, these missions have transformed the CMB from a curiosity into the most powerful tool we have for studying the universe. As the photons of the cosmic microwave background travel through the universe, they occasionally pass through galaxy clusters, where they interact with the hot gas in the intracluster medium. This interaction, known as the Sunyaev-Zeldovich effect, causes some of the CMB photons to gain energy, shifting them to shorter wavelengths and creating a shadow or distortion in the CMB in the direction of the cluster. The effect is subtle, but it can be detected with sensitive instruments, and it provides a way to study galaxy clusters that is independent of their distance. Because the Sunyaev-Zeldovich effect depends on the density and temperature of the gas, rather than on the emission of light, it can be used to detect clusters that are too distant or too faint to be seen in optical or X-ray surveys. It also provides a way to measure the Hubble constant and the properties of dark energy by counting the number of clusters as a function of redshift and comparing it to theoretical predictions. The Sunyaev-Zeldovich effect is a reminder that the cosmic microwave background is not just a relic of the early universe, but a dynamic screen that is constantly being modified by the structures it passes through. Another subtle effect imprinted on the cosmic microwave background is the integrated Sachs-Wolf effect, which arises from the interaction of CMB photons with the evolving gravitational potential of large-scale structures. As a photon falls into a gravitational well, such as a galaxy cluster or a supercluster, it gains energy and is blue-shifted. As it climbs out of the well, it loses energy and is redshifted. In a static universe, these two effects would cancel out, and there would be no net change in the photon's energy. But in an expanding universe dominated by dark energy, the gravitational wells are changing over time. They are becoming shallower as dark energy drives the acceleration of the expansion. This means that a photon climbing out of a well loses less energy than it gained falling in, resulting in a net blue shift. By correlating the temperature fluctuations in the CMB with the distribution of galaxies and large-scale structures, astronomers have detected the integrated Sachs-Wolf effect, providing independent evidence for the existence of dark energy and its influence on the evolution of cosmic structure. The cosmic microwave background serves as a cosmic ruler, a standard measuring stick that allows astronomers to determine distances and scales across the universe. The characteristic size of the fluctuations in the CMB, the angular scale of the first acoustic peak, depends on the geometry of the universe and the distance to the surface of last scattering. By measuring this angular scale with high precision, cosmologists can determine whether the universe is flat, positively curved, or negatively curved, and they can calibrate the cosmic distance ladder, the series of methods used to measure distances to faraway objects. The CMB also provides a way to measure the Hubble constant, the current rate of expansion of the universe, by comparing the distance to the surface of last scattering inferred from the CMB with the redshift of that surface. This measurement is independent of other methods, such as those based on supernovae or Cepheid variable stars, and it has revealed a tension between different measurements of the Hubble constant, a puzzle that is currently one of the most active areas of research in cosmology. As you close your eyes and let your thoughts drift into the vastness of the cosmos, imagine the cosmic microwave background as a gentle, all-encompassing glow, a whisper of light that has been traveling through space for nearly 14 billion years. It is the echo of the beginning, the afterglow of the moment when the universe became transparent, and it surrounds us on all sides, a constant reminder of our cosmic origins. This ancient light carries within it the story of the universe, its age, its composition, its geometry, its fate, all encoded in the subtle patterns of temperature and polarization that fill the sky. The cosmic microwave background is a gift from the early universe, a message sent across the eons, and it is one of the most beautiful and profound discoveries in the history of science. Rest now in the knowledge that the universe is knowable, that its secrets can be read in the light that fills the sky, and that we are part of a cosmic story that began with a flash of light and will continue for trillions of years to come. Sleep well, and let the ancient glow of the cosmos guide you into dreams. We turn now to one of the most profound concepts in all of physics, a principle that governs the flow of time itself and determines the ultimate fate of every star, every galaxy, and every structure in the universe. Entropy is the measure of disorder, the tendency of organized systems to break down and dissipate into chaos. And it is the reason why time has a direction, why we remember the past, but not the future, why eggs break, but do not spontaneously reassemble. Tonight we will explore the role of entropy in the cosmos, from the formation of black holes, the most entropic objects in the universe, to the slow, inexorable fade of order as the cosmos ages, and we will discover that the arrow of time points toward a future of increasing darkness and stillness. The second law of thermodynamics is one of the most fundamental principles in physics, and it states that in any closed system, entropy, the measure of disorder or randomness, always increases over time, or at best remains constant. This law is the reason why heat flows from hot objects to cold objects, why gases expand to fill their containers, and why complex structures eventually decay. In the context of the universe, the second law means that the cosmos is constantly moving from a state of lower entropy to a state of higher entropy, from order to disorder, from structure to uniformity. In the early universe, entropy was relatively low. Matter and energy were distributed in a highly organized way, with distinct regions of different densities and temperatures. But as the universe has evolved, entropy has increased, and it will continue to increase until the cosmos reaches a state of maximum entropy, a condition known as thermodynamic equilibrium, where no further change is possible and all processes come to a halt. This is the ultimate fate predicted by the second law, a state of perfect uniformity and stillness, where the universe has exhausted all its capacity for change and exists in a timeless, unchanging equilibrium. Black holes are the most extreme manifestations of entropy in the universe, objects so dense that their gravitational pull is strong enough to trap even light itself. When a massive star exhausts its nuclear fuel and can no longer support itself against gravity, it collapses, and if the core is massive enough, it continues collapsing past the point of no return, forming a black hole. The boundary of a black hole is called the event horizon, the point beyond which nothing, not even light, can escape. From the outside, a black hole appears as a perfectly dark sphere, a void in space that swallows everything that comes too close. But black holes are not just cosmic vacuum cleaners. They are also the most entropic objects in the universe. In the 1970s, physicist Jacob Bekenstein proposed that black holes have entropy, and that this entropy is proportional to the area of the event horizon, not the volume. This was a radical idea, because it suggested that the information content of a black hole is encoded on its surface, rather than in its interior, a concept that has profound implications for our understanding of quantum mechanics and gravity. Stephen Hawking later showed that black holes also have a temperature, and that they emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This means that black holes are not entirely black, but glow faintly with thermal radiation, and over immense timescales, they will eventually evaporate, returning their mass and entropy to the universe. The discovery that black holes emit Hawking radiation led to one of the deepest puzzles in theoretical physics, known as the black hole information paradox. According to quantum mechanics, information is never truly lost. The state of a system at any given time is determined by its state at an earlier time, and in principle, you can reconstruct the past from the present. But when a black hole evaporates, it seems to destroy information, because the Hawking radiation it emits is thermal, random, and carries no information about what fell into the black hole. This appears to violate the fundamental principles of quantum mechanics, creating a paradox. For decades, physicists have debated how to resolve this paradox, and the leading idea is that information is not lost, but is somehow encoded in the Hawking radiation in a way that is extremely subtle and difficult to detect. This has led to the development of new ideas about the nature of space-time, such as the holographic principle, which suggests that all the information in a volume of space can be encoded on the boundary of that volume, like a hologram. The information paradox remains one of the great unsolved problems in physics, a puzzle that sits at the intersection of quantum mechanics, general relativity, and thermodynamics. Entropy is intimately connected to the arrow of time, the fact that time has a direction flowing from past to future. In the fundamental laws of physics, time is symmetric. The equations work equally well whether time runs forward or backward. But in our everyday experience, time has a clear direction. We remember the past but not the future. We see glasses shatter but not reassemble. We grow older but not younger. This asymmetry is a consequence of the second law of thermodynamics. Entropy increases over time, and this increase defines the direction of time's arrow. In the early universe, entropy was low, and there was a great deal of order and structure. As time has passed, entropy has increased, and the universe has become more disordered. The arrow of time points in the direction of increasing entropy, from the organized past to the chaotic future. This raises a profound question. Why was the entropy of the early universe so low? Why did the universe begin in such a highly ordered state? This is one of the deepest mysteries in cosmology, and it suggests that the Big Bang was not a random event, but a very special low-entropy initial condition, the origin of which we do not yet understand. Stars are engines of entropy production, converting the low-entropy energy stored in nuclear fuel into high-entropy heat and light. When a star forms from a collapsing cloud of gas, it is in a relatively low-entropy state, with matter concentrated in a small region and nuclear reactions proceeding in an organized way. But as the star burns its fuel, it radiates energy into space, increasing the entropy of the surrounding universe. When the star dies, whether in a supernova explosion or a more gradual process, it disperses its material into the interstellar medium, further increasing entropy. The remnants of stellar death, white dwarfs, neutron stars, and black holes are high-entropy objects, the final resting states of matter that has exhausted its capacity for further nuclear reactions. Over trillions of years, all the stars in the universe will die, and the cosmos will be filled with these stellar remnants, along with the diffuse radiation they have emitted. This is the slow fade of order, the gradual increase of entropy that will eventually leave the universe in a state of maximum disorder, with no remaining sources of energy to drive further change. Even black holes, the most stable and long-lived objects in the universe, are not eternal. Through the process of Hawking radiation, black holes slowly lose mass, emitting particles and energy into the surrounding space. The rate of evaporation is inversely proportional to the mass of the black hole. Small black holes evaporate quickly, while massive black holes evaporate very slowly. A black hole with the mass of the Sun would take about 10 circumflex, 67 years to evaporate, an unimaginably long time, far longer than the current age of the universe. But a supermassive black hole, with a mass of billions of suns, would take even longer, on the order of 10 circumflex 100 years or more. Eventually, though, all black holes will evaporate, leaving behind only a faint glow of radiation and a universe that is slightly more disordered than before. The evaporation of black holes represents the final stage in the increase of entropy, the point at which even the most concentrated forms of matter and energy have been dispersed into the void. After the last black hole evaporates, the universe will be filled with a thin soup of photons and other particles, all at nearly the same temperature, in a state of near-perfect thermodynamic equilibrium. The ultimate fate of the universe, according to the second law of thermodynamics, is a state known as heat death, or the Big Freeze. In this scenario, the universe continues to expand forever, driven by dark energy. And as it expands, all the stars burn out, all the black holes evaporate, and all the matter and energy in the cosmos are dispersed into a thin, uniform haze. The temperature of the universe approaches absolute zero, and there are no remaining gradients of temperature or density to drive any processes. Everything is in thermodynamic equilibrium, and no further change is possible. This is a state of maximum entropy, a condition of perfect uniformity and stillness, where time, in a sense, ceases to have meaning, because there are no events, no changes, no processes to mark its passage. The heat death is not a violent end, but a slow, gentle fade into darkness and silence, a cosmic twilight that lasts for eternity. It is a profoundly peaceful vision of the end, a universe that has exhausted all its energy and settled into a final, unchanging rest. In some theories of particle physics, protons, the building blocks of atomic nuclei, are not stable, but decay over extremely long timescales, on the order of 10 circumflex 34 years or more. If protons do decay, then even the most stable forms of matter will eventually dissolve, breaking down into lighter particles such as positrons, neutrinos, and photons. This would mean that, given enough time, all the atoms in the universe would disintegrate, leaving behind only radiation and a few exotic particles. The decay of protons would represent a further increase in entropy, as the organized structure of atomic nuclei is broken down into a more disordered state. So far, experiments have not detected proton decay, and the current lower limit on the proton lifetime is about 10 circumflex 34 years. But if it does occur, it would be one of the final stages in the dissolution of matter, a step toward the ultimate heat death of the universe. Even if protons are stable, the evaporation of black holes and the expansion of the universe will eventually leave the cosmos in a state where matter is so dispersed and diluted that it is effectively non-existent, a universe of pure radiation and empty space. Dark energy, the mysterious force driving the accelerated expansion of the universe, also plays a role in the increase of entropy. As the universe expands, the energy density of matter and radiation decreases because the same amount of energy is spread over a larger volume. But the energy density of dark energy, if it is a cosmological constant, remains constant, which means that the total amount of dark energy in the universe is increasing as space expands. This increase in dark energy contributes to the overall increase in entropy because it represents a form of energy that is uniformly distributed and cannot be used to do work or drive processes. In a universe dominated by dark energy, the expansion accelerates and structures become increasingly isolated from one another, unable to interact or exchange energy. This isolation is another form of entropy increase as the universe becomes more and more fragmented, with each region evolving independently, cut off from the rest of the cosmos by the relentless expansion of space. One of the most profound questions in cosmology is what happens to information as the universe evolves toward a state of maximum entropy. According to the laws of quantum mechanics, information is conserved. It cannot be created or destroyed, only transformed. But in a universe that is heading toward heat death, where all structure and order have been erased, where does the information go? Is it preserved in some subtle form, encoded in the correlations between particles, or is it lost forever, swallowed by the increasing entropy? The black hole information paradox is a microcosm of this larger question, and resolving it may require a new understanding of the relationship between entropy, information, and the fundamental laws of physics. Some physicists have speculated that the universe itself might be a kind of hologram, with all the information about its contents encoded on a distant boundary, preserved even as the interior evolves towards maximum entropy. These are deep and speculative ideas, but they hint at the possibility that the story of the universe is not one of simple decay and loss, but of transformation and preservation in ways we do not yet fully understand. As you drift towards sleep, let yourself contemplate the slow, inexorable increase of entropy, the gentle fade of order into chaos, the transformation of the vibrant, structured universe into a state of perfect stillness and uniformity. There is acquired dignity in this process, a natural progression from complexity to simplicity, from motion to rest. Entropy is not an enemy, but a fundamental aspect of the cosmos, the force that allows change to occur, that gives time its direction, that makes the universe a dynamic, evolving system rather than a static, frozen tableau. The stars will burn out, the black holes will evaporate, and the universe will grow cold and dark. But this is not a tragedy. It is the natural conclusion of a story that began with the Big Bang, a story of energy and matter, of structure and transformation, of light and darkness. Rest now in the knowledge that the universe is following its course, that the laws of thermodynamics are guiding it toward its ultimate fate, and that in the vast expanse of time, there is room for both creation and dissolution, for both order and entropy. Sleep well, and let the slow fade of the cosmos carry you into dreams of eternal peace. We arrive now at the final chapter of our cosmic journey, contemplating the ultimate fate of the universe in the unimaginably distant future. This is not a story of violent endings or catastrophic collapses, but of a slow, gentle transition into a state of perfect stillness and silence, a cosmic peace that will endure for eternity. The heat death of the universe is the final destination toward which all of existence is moving, a state of maximum entropy where all processes have ceased, all energy has been dispersed, and time itself loses its meaning. Tonight, we will explore this distant future, tracing the final stages of cosmic evolution, and discovering that the end of the universe is not darkness and despair, but a profound and eternal tranquility. We currently live in what cosmologists call the stelliferous era, the age of stars, a time when the universe is filled with galaxies, each containing billions of stars that shine brightly against the darkness of space. But this era will not last forever. Stars form from clouds of gas, primarily hydrogen and helium, and they burn through this fuel over millions or billions of years, depending on their mass. As time passes, the supply of gas available for star formation is gradually depleted, consumed by existing stars, or locked away in stellar remnants like white dwarfs, neutron stars, and black holes. Current estimates suggest that star formation will peak and then decline over the next few trillion years, and by about 100 trillion years from now, the last stars will have formed. After that, the universe will enter a new era, one in which no new stars are born, and the existing stars slowly burn out, one by one, leaving behind a cosmos that grows progressively darker and colder. The stelliferous era, which has lasted for about 13.8 billion years so far, is just a brief moment in the vast expanse of cosmic time, a fleeting age of light and warmth in a universe that will spend most of its existence in darkness. After the last stars have burned out, the universe will enter the degenerate era, named for the degenerate matter that makes up white dwarfs and neutron stars, stellar remnants in which matter is compressed to extraordinary densities. During this era, which will last from about 10 circumflex 14 to 10 circumflex 40 years after the Big Bang, the universe will be populated primarily by these stellar corpses, along with brown dwarfs, failed stars that never ignited nuclear fusion, planets, and black holes. There will be no sources of light, except for the faint glow of cooling white dwarfs and the occasional flash of radiation from matter falling into black holes. The universe will be a dark, cold place, with temperatures approaching absolute zero. Galaxies will still exist, but they will be invisible, their stars replaced by dark remnants. Over time, even these remnants will fade, as white dwarfs cool and become black dwarfs, cold, dark objects that emit no light at all. The degenerate era is a time of slow decay, as the structures built up during the stelliferous era gradually dissolve, and the universe moves inexorably toward a state of greater disorder and uniformity. Even the galaxies themselves are not eternal. Over trillions of years, the stars and stellar remnants within galaxies will interact gravitationally, and through a process called dynamical relaxation, some will be ejected from the galaxy entirely, while others will spiral inward toward the central black hole. This process is incredibly slow, taking on the order of 10 circumflex, 19 to 10 circumflex, 20 years. But given enough time, galaxies will gradually evaporate, losing most of their mass to the intergalactic void. The stars and remnants that are not ejected will eventually be swallowed by the supermassive black hole at the galaxy's center, which will grow in mass as it consumes the surrounding material. By the end of the degenerate era, most galaxies will have dissolved, leaving behind isolated black holes and a sparse scattering of ejected stellar remnants, drifting alone through the expanding void. This dissolution is another manifestation of the increase in entropy, as the organized structure of galaxies breaks down into a more disordered state, with matter dispersed over ever larger volumes of space. After the degenerate era comes the black hole era, which will last from about 10 circumflex 40 to 10 circumflex 100 years. after the Big Bang. During this era, black holes will be the dominant objects in the universe, the last remaining concentrations of mass in an otherwise empty and expanding cosmos. These black holes will range in size from stellar mass black holes formed from the collapse of massive stars to supermassive black holes, with masses of billions or even trillions of suns formed from the merger of smaller black holes and the accretion of matter over cosmic time. The universe will be almost entirely dark, with no stars, no galaxies, and no sources of light, except for the faint Hawking radiation emitted by the black holes themselves. This radiation is incredibly weak. A black hole with the mass of the Sun emits Hawking radiation with a temperature of about 60 billionths of a degree above absolute zero. But it is the only process by which black holes lose mass. Over unimaginably long timescales, this radiation will cause the black holes to evaporate, slowly shrinking until they finally disappear in a brief flash of energy. The black hole era is a time of profound stillness, a universe in which almost nothing happens, where the only events are the slow, steady evaporation of black holes and the relentless expansion of space. The evaporation of black holes is the final act in the story of matter and energy in the universe. As a black hole loses mass through Hawking radiation, its temperature increases, and it evaporates faster and faster in a runaway process that ends with a final burst of radiation. For a stellar mass black hole, this process takes about 10 circumflex 67 years. For a supermassive black hole with 1 billion solar masses, it takes about 10 circumflex 100 years. When the last black hole evaporates, the universe will be left with nothing but a thin soup of photons, neutrinos, and other particles, all at nearly the same temperature, in a state of near-perfect thermodynamic equilibrium. This is the final light, the last energy released into the cosmos, and after it fades, there will be no further sources of energy, no further processes, no further change. The universe will have reached a state of maximum entropy, a condition from which no further evolution is possible. This is the ultimate peace, the final stillness, the end of the cosmic story. After the last black hole has evaporated, the universe will enter the dark era, which will last forever. During this era, the universe will be filled with a diffuse gas of photons and other particles, all at a temperature just above absolute zero, spread across an ever-expanding volume of space. There will be no stars, no planets, no black holes, no structures of any kind, just a uniform, featureless expanse of nearly empty space. The expansion of the universe, driven by dark energy, will continue, and the distance between any two particles will grow without limit, until eventually each particle is alone in its own cosmic horizon, unable to interact with any other particle. This is the heat death, the big freeze, the final state of the universe, as predicted by our current understanding of cosmology. It is a state of perfect stillness and silence, where nothing happens, where time has no meaning, where the universe exists in an eternal, unchanging equilibrium. There is a profound peace in this vision, a sense of completion, of a story that has reached its natural conclusion. If protons are not stable, but decay over timescales of 10 circumflex 34 years or more, then the dark era will be preceded by an era of matter dissolution, in which all the atoms in the universe break down into lighter particles. This would mean that even the stellar remnants and planets that survive into the degenerate era will eventually disintegrate, leaving behind only radiation and a few exotic particles. The decay of protons would represent a further step toward maximum entropy, as the last vestiges of organized matter are erased. If protons do decay, the universe will reach its final state even sooner, with all matter converted into radiation and the cosmos settling into thermodynamic equilibrium. So far, experiments have not detected proton decay, but if it occurs, it would be one of the final chapters in the story of the universe, a last transformation before the eternal stillness of the dark era. Dark energy, the mysterious force driving the accelerated expansion of the universe, will play a crucial role in the far future. If dark energy is a cosmological constant, as current observations suggest, then its energy density will remain constant as the universe expands, and the expansion will continue to accelerate forever. This means that the universe will grow larger and larger, colder and colder, with the distance between any 2 points increasing without limit. Eventually, the observable universe will shrink to include only the local region of space, as distant galaxies and structures are carried away by the expansion and disappear beyond the cosmic horizon. If dark energy is not constant, but instead grows stronger over time, the expansion could accelerate even faster, leading to a more dramatic end known as the Big Rip, in which the fabric of space itself is torn apart. But if dark energy remains constant, the universe will simply expand forever, growing ever more diffuse and empty, until it reaches the state of maximum entropy that characterizes the dark era. Even in the dark era, when the universe has reached a state of near-perfect thermodynamic equilibrium, it will not be entirely empty. The quantum vacuum, the lowest energy state of space, is filled with virtual particles that constantly pop in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating. These quantum fluctuations are a fundamental feature of the universe, a consequence of the Heisenberg uncertainty principle, and they will persist even in the far future, when all other processes have ceased. In a sense, the vacuum is never truly empty, but is always seething with activity on the smallest scales. These fluctuations are incredibly subtle, and they do not produce any macroscopic effects. But they are a reminder that even in the ultimate stillness of the dark era, the universe retains a faint spark of dynamism, a whisper of the quantum realm that underlies all of reality. In the dark era, when the universe has reached maximum entropy and all processes have ceased, time will lose its meaning in a profound way. The arrow of time, which is defined by the increase of entropy, will no longer point in any direction, because entropy will have reached its maximum value and can increase no further. Without change, without events, without processes to mark the passage of time, the universe will exist in a kind of eternal now, a timeless state in which past, present, and future are indistinguishable. This is not the same as the absence of time, but rather a state in which time exists, but has no content, no structure, no direction. It is a deeply philosophical concept, one that challenges our intuitions about the nature of time and existence. In this eternal now, the universe will rest, unchanging and unchangeable, a monument to the journey it has taken from the Big Bang to the heat death, from the primordial silence to the ultimate peace. As you close your eyes and let your mind drift into the far future, imagine the universe in its final state, a vast, dark, silent expanse, filled with nothing but the faint glow of the quantum vacuum and the gentle expansion of space. There is a profound beauty in this vision, a sense of completion and fulfillment, of a story that has been told in full. The universe has lived its life, from the explosive birth of the Big Bang to the slow, gentle fade of the heat death, and it has given rise to stars and galaxies, to planets and life, to consciousness and wonder. The fact that it will end in stillness and silence does not diminish the beauty of what has come before. Rather, it gives that beauty a poignant depth, a reminder that all things are temporary, that all structures eventually dissolve, that all light eventually fades. But in the vast expanse of time between the beginning and the end, there is room for infinite complexity, infinite possibility. The universe is a gift, a brief moment of order and structure in the eternal flow of entropy, and we are privileged to be part of it, to witness its wonders, to contemplate its mysteries. And so, as you drift towards sleep, let yourself rest in the knowledge of the ultimate peace that awaits the universe. The heat death is not an ending to be feared, but a natural conclusion, a return to the stillness from which everything emerged. In the beginning there was silence, and in the end there will be silence again. But in between there has been light and warmth, structure and change, beauty and wonder. The universe is following its course, guided by the laws of physics, moving inexorably towards its final state. And there is a deep tranquility in accepting this fate, in understanding that the cosmos is not eternal, but is a finite story with a beginning, a middle, and an end. Sleep now, and let the eternal stillness of the far future carry you into dreams of peace and rest. Know that you are part of this cosmic journey, that the atoms in your body were forged in the hearts of stars, that you are connected to the universe in the most fundamental way, and that when you close your eyes and drift into sleep, you are participating in the same process of rest and renewal that will one day embrace the entire cosmos. Sleep well and dream of the infinite peace that lies at the end of time.